So I'm Mike Chandler from the University of Edinburgh, although the experimental work presented here was mostly conducted at the University of Manchester Rock Deformation Lab, and it involves some stress-sensitive permeability measurements on samples from the UK GEOS GGCO1 borehole that Andreas, Dave, and Ellie Maria just talked about. Particularly because as Dan, Andreas, and Dave spoke about, there's a variety of different kind of stress situations that rocks might be under in a mine water geothermal system that we need to understand the permeability of sort of flow through. So for instance, rubble within a mine shaft is essentially unconfined. The rocks kind of within the wall that are discussed for kind of regional heat transfer are essentially under the stress state of the depth and the rock, and the kind of the rocks within the wall of the mine shaft itself are sort of partially under confinement, but partially not due to the presence of the mine shaft itself. So there's quite a few complicated situations going on there. So I won't go back over what the Glasgow UK GEOS Observatory is, but this is the site that we gained samples from. And the rock samples that I have are from the Glasgow main coal, Glasgow mudstone. Well, I've just called these the Glasgow mudstone and sandstone. They're the mudstone and sandstone that directly underlie the Glasgow main coal at a depth of about 130 meters. What we've done essentially is I've made stress-sensitive permeability measurements by taking core samples of these with 1 inch diameter and 2 inches of length, and I've put them under some hydrostatic confinement, and I've measured the permeability through them using a method called the oscillating pore pressure method. So essentially this rock is under confinement and there is no way for fluid to travel from one end to the other than through the rock. Then I use a piston at this end to drive a sinusoidal signal into in the pore pressure into this end of the rock, and I measure the pore pressure at the far end of the rock. And what you tend to get is a plot that looks something like this. So in the red is the pore pressure that I'm driving at one end of the rock, sinusoid, in this case with a mean pressure of about 2.95 MPa. And at the far end of the rock, you'll measure a signal with the same frequency, but an attenuated amplitude and some phase shift. And you can go about calculating the permeability of the rock material through the attenuation and the phase shift of these two signals. So if I do this at a variety of different confining pressures and pore pressures, I can measure the variation of the permeability of the rock with the effective pressure of the system. So plotted here on the right, I have measurements of these permeabilities as a function of effective pressure. That's the Terzaghi effective pressure, so just the confining pressure minus the mean pore pressure of that oscillating signal for those various rock samples. And you should note that this is a logarithmic permeability axis. So we can see that the sandstone is high permeability and almost completely insensitive to the stress state. You can see that the yellow and green, the Glasgow mudstone, at low effective pressures, the permeability parallel to bedding is significantly higher to perpendicular to bedding, but at higher effective pressures, it becomes largely isotropic. And also after we've cycled the stress up and down a bit, the fractures that are lying parallel to bedding start to close up, and this becomes more isotropic even at low effective pressures. And you can see that the coal is fairly stress sensitive in terms of the permeability measured, and also it's very hysteretical in that every time we cycle the pressure up and down again, the permeability we then measure at the same pressures we were at before has fallen. So it's common to fit stress-sensitive permeability by an exponential of this form, K equals K naught times the exponential of the effective pressure. And usually you would use the Terzaghi effective pressure, but this doesn't account for any differences in sensitivity to the pore and confining pressure of the rock. So Bio in 1941 introduced a constant which addresses this difference. And essentially it's a redefinition of the effective pressure to account for a situation where the rock experiences pore pressure differently to confining pressure. And I won't go through this maths, but we can measure these different parameters from a series of the stress sensitive permeability measurements in the rock. And if we do so, we find that basically, so the more stress sensitive the permeability is, the higher the absolute of this number gamma is. So we can see that for instance, the coal is more stress sensitive than the mudstone. And then the second thing we can see is that when K, the permeability is more sensitive to change in pore pressure than it is to changes in confining pressure, then this number chi is above 1. And conversely, when it's more sensitive to pore pressure than confining pressure, this number, when it's less sensitive to pore pressure than confining pressure, this number chi will be below 1. So firstly, the fact that this number is higher in the two coals than it is in the mudstones means that the coal is in fact even more stress sensitive than mudstones in terms of the permeability that's measured. And then the fact that these numbers are all below 1 suggests that the permeability is more influenced by the pore pressure than it is by the confining pressure in these rocks. And these numbers are lower in the mudstone than coal, perhaps. So the mudstone permeability is more sensitive to the pore pressure than in the coals. So just to give one idea of how you could use this number at a large scale, the Packlet number is a dimensionless quantity that describes the ratio of the advective to conductive heat transfer in a rock. And Q in this definition is some subsurface flow rate and L is some characteristic length. So when this number is of the order of 1, groundwater movements begin to affect the subsurface temperature field. So if I substitute in Darcy's law to this definition, we get something that looks a bit like this. And essentially, this is defining the Packlet number in terms of L, a load of constants, the hydraulic head gradient, and K, which is this stress-sensitive permeability we've measured. So just to quickly explain where I pulled some of these constants from, I've taken a very approximate hydraulic head gradient just from the distances between the boreholes and the ambient hydraulic head that was measured on this date and was published in this paper. And I've taken thermal conductivity and volumetric heat capacity values just by calculating the geometric means from XRD volume components. And I will note that the effective conductivity that I've measured, well, not measured, that I've determined for the coal in this sense is much higher than that Dave just presented from direct measurements. So there's perhaps something I need to think about there. Obviously, I would tend to assume the direct measurement is correct rather than just a determination from the mineralogy. Anyway, so if I then go about rearranging this equation again, just to get that L value, which is the characteristic length of the system, and then set the Packlet number equal to 1, what you'll have is a value of the characteristic length of the system above which groundwater movements start to become significant in altering the subsurface temperature field. So when I do that, I end up with an equation that looks like this, and these are all various, so these numbers I can put in from those XRD mineralogies. I've got a very approximate hydraulic head gradient from the field, and these are just numbers for water, and then my stress sensitive permeability is down here. And if you substitute them in, you can get the essentially what distance scale the advective heat transport will start to become important on for various different pressures in the different rocks. And you can see that this is very stress sensitive, but also it's extremely high. We're looking at distance scales on the order of 10 to the 7 meters, which is, well, very high. So that suggests that for kind of regional advective heat transfer, these measures of permeability are probably not completely appropriate. And that's perhaps understandable in that obviously the largest scale floor I can have in a 1-inch diameter sample is 1 inch. So it's kind of telling us that for a much larger scale regional heat transport, the majority of flow is happening in conduits that are larger than 1 inch in scale. So to summarize, stress-sensitive permeability was measured in core materials from around the Glasgow main coal in well GGC01. There's a variety of different stress states and length scales that are relevant in mine water geothermal energy systems. The coals were found to be more stress-sensitive than the shales, and they're each much more sensitive than the sandstones in terms of permeability. The shale was very anisotropic at low stress, but essentially isotropic after hysteresis, so cycling of the pressures. And these low permeabilities suggest that advection will have little effect over heat transfer over reasonable length scales, but that's perhaps more a suggestion that these measures of permeability shouldn't be used at that scale without some kind of modeling to add the impact of kind of larger scale fractures. So yeah. Thanks for listening. You can contact me at this email address, or the raw data that I presented here is available on the UK Geos site, and this is the data set number. Thanks.